5 minutes. Then we will start.
So you're all set. You're all set.
Yeah, everything is fine. And in 5 minutes, we are just waiting on a lead and yeah. Great. Thank you a lot.
Enjoy.
See you later. We are not used to that. Okay, so yeah.
Questions will be answered.
Okay.
Yeah. So we could go all put them on the screen, or I can log into Zoom and show you the chat on my phone.
Okay. They will be two session chairs, Claudio and then Antonio.
Okay.
So what do you prefer? Project it on the screen, or he could show you the questions and
show that. Yeah, show you the questions. Okay.
Okay.
Okay. Do you hear me? Good morning, everyone. And now we are starting the second part of our KaRS and ComplexRec joint workshop. This year, you've seen that we have merged the two workshops, the ComplexRec one at its 5th edition and our KaRS workshop at its 3rd edition. And we were able to organize a very successful workshop with all these organizers that you can see there. And I want to thank them one by one. So I would like to thank Iman, Tuan, Bamshad, Casper, and Sole, Pierpaolo, Tommaso, Francesco, Cataldo, Lucio, and Marcus. And thanks to them, we were able to collect a lot of interesting submissions and papers that we can share with you, and we can chat and create a very interesting debate. And this happened in the first part of our workshop during the virtual day on Saturday. Then we can see together some of the most important objectives of the ComplexRec workshop. So to have recommender systems that focus on complex inputs. So they could be active user inputs like different kind of interactions or complex environments, and the usage of features or attributes and so on. But also the ComplexRec workshop focus on what we could denote as complex outputs. So the way in which we can prepare the final recommendation. So we can package them, or maybe we could have composite items. And as you can imagine, all these kind of submission, all these kind of contributions will be really, really important in practical recommendation. On the other hand, the goal of KaRS, so knowledge aware and conversational recommender systems, is to focus on another kind of recommender systems. So all the recommender systems that makes use of knowledge in a way or in another. So maybe with the knowledge graphs, or maybe with some textual information that should be analyzed to prepare meaningful suggestions. And also the other half, and now an increasingly important half of the KaRS workshop is related to conversational recommender systems. This is a new paradigm, and more or less all the big companies now are working on handling how to suggest new items based on an ongoing conversation. So with the conversational recommender system, there are a lot of new challenges that are posed to the RecSys community. And now some information. You have seen that our workshop this year is a hybrid workshop. So we will try to propose a blended way of living together workshop. So we have remote audience, and now today we have also physical audience. So we will do our best to connect the remote audience with the physical one, and we will read all the possible questions that we receive from the physical and the remote audience. To do that, I suggest the remote attendees to write your questions in the chat of your Zoom meeting, so that we can read all your questions live and ask them to the presenter. This year, we accepted a very high number of papers. So we accepted 11 long papers, 3 short papers, and 3 position papers. And obviously, we are already working on the proceedings with the CRWS. And as soon as we have the final link of the proceedings, we will make it available for everybody. Oh. Okay. We have already passed all the sessions that were prepared for the virtual part of the workshop, and today and during that part we had a very interesting keynote from Edward Malthaus, and today we will focus on another kind of program. Today we will give the word to our keynote speaker, Gerard De Melo, and after that we will have a couple of papers for the end of our first session. Then we will have a break, and then again we will have a full session with the 7 papers, and then we will wrap up with all the consideration that we can do after this exciting workshop. So you can see now the keynote speaker, Gerard De Melo. I'm not going to give you any information about him because many of you already know him, and also because the first session chair will introduce him properly. So again, we are really excited to share with you this workshop, and have a good day and have a good workshop. Enjoy the workshop. And please, Claudio, come here. So Claudio is the first session chair. A big clap to Claudio.
Good morning. Can you hear me? Yes. It's a pleasure to introduce Professor Gerard De Melo. Gerard De Melo is a full professor at the Hasso-Plattner Institute for Digital Engineering at the University of Potsdam, Germany. And he's published a lot of papers, over than 150, and with several awards with the best paper. And in this talk, Gerard discussed several methods to bring together various kinds of knowledge and neurosymbolic explainable AI. So Gerard, please, and thank you.
All right. Thank you for inviting me. I hope you can see my slides. Right.
Yes.
Okay, so let's get started. The title of my talk is How Can I Help You? Knowledge Graphs for Explainable Recommendation. It's going to be a bit broader than just knowledge graphs. I'm going to be talking about a bunch of different ways to combine different sources of information to provide background knowledge into recommendation. And so to get started, if we think about the traditional way algorithms are thought, we typically have some sort of input, and then this input gets fed into the algorithm, and then based on this, we produce some output. That's the typical way you think about computational algorithms. But nowadays, modern information systems are very different from this traditional paradigm. So when I ask Siri to do something for me or recommend some restaurant for me, the input is not just my utterance, the thing I provide to the system as a voice input. Actually, the system needs access to all of the world's data, basically, everything we can access online, including services that could be interactive. And so in this talk, I'll be talking about this way of bringing together different sources of information where you go beyond just the original inputs. You have additional textual data, you can have additional structured data, and you can also have multimodal data. So this is basically the way all modern user facing information systems are operating, and the truly modern information systems also place a greater emphasis in incorporating the user in the loop, basically a human in the loop process where the human and the system collaboratively solve some problem together. And so I'm going to be giving some examples of this from our research. The first section is going to be about knowledge-driven font recommendation. Then I'll talk about, this is the major part of the talk, about using knowledge graphs for explainable recommender systems. And then finally, I also have a smaller section about conversational recommendation. So let's get started with the first part. This is joint work, mostly with Tuba Kulacholu, who was a PhD student of mine at Rutgers University, and she's now at Google. So some of you might be asking, why font recommendation? This is not one of the typical scenarios we study when we deal with recommender systems. Well, it's actually an important field, or an important task, at least. There are over 100,000 fonts now available online, but yet most of us typically just keep using the same 3 to 5 fonts for everything we do. And in many cases, that is fine, but there are a lot of people who want to better exploit the diversity of fonts available online. This is particularly important if you're a graphic designer or you work in marketing, because there are many studies that show that which font you choose can affect the brand credibility that people associate with the product, the price expectations that people have about a product. It can also affect whether someone intends to purchase a product, and it can even go beyond that by licensing certain associations with the product itself. So certain fonts lead to certain kinds of assumptions about how sweet the product is. Or if you're looking at an email, people make a lot of assumptions about the personality of a person when they see an email written in a non-conventional font. So it can be quite important to choose the right font. A very nice example of a font that incorporates specific aspects of the product is this Gillette logo, where you can see the blades shape in the font quite explicitly, but there are a lot more subtle cues that people pick up on. So for example, rounder shapes lead to certain assumptions about personality or sweetness of a food product. So how do we achieve font recommendation? And here we get back to this introductory slide that I had, that you need to basically combine different sources of information. This is where you need a knowledge-driven system that brings together different kinds of input. And what we did in our work was we collected a whole bunch of font-related knowledge first. So we collected a knowledge graph, you could say. It's not a real knowledge graph. It's mostly a data set of over 10,000 different fonts. These are labeled with tags on this website, over 2,600 different tag types and over 54,000 font tag assignments. Then we started off by using this sort of data and learning representations of the fonts. So we started with the visual part of a font. We have the actual font files, so we can try to learn things about their appearance. And to do that, we simply render small little images and then use a convolutional neural network to learn vector representations of these different images. And with that, we get a visual representation space. So basically fonts that are similar visually have similar embeddings. Next, what we do is we connect this with further modalities. So in particular, we add textual information from word embeddings. There's actually some more details in this whole process where we exploit background knowledge to process the word embeddings and make them more semantic. I won't go into those details here. But the most important part is bringing together different kinds of modalities. And that we do in a cross-modal alignment step where we align these two vector spaces basically by normalizing and whitening the matrices, the embedding matrices, and then learning an orthogonal transformation matrix. And with this, we then get a cross-modal vector space where we can connect fonts and words in the same space. And so this allows us to already recommend fonts for given query keywords. And this can be done for very visual keywords, such as in this one study, where we actually used another crowdsourced data set to get good results. Human seed data set was used to induce new ratings for arbitrary fonts. But we can also actually go beyond this. And for any query keyword, any concept word, we can actually find fonts that somehow reflect the contents of that word. So for daughter, we have some more elegant fonts. For guilty, we have some more serious fonts. And we can do the same thing actually for color. And this is mediated via the emotions we associate with words. And as one application, we also generate word clouds. So you can see here on the left side, playful word cloud with a colorful color palette for the Smurfs movie, actually. And then on the right side, for the movie Scream, which is more of a horror movie. So there you use very different fonts and colors. So this was a first step, but we can also go further and go towards more complex scenarios where we bring in humans in the loop. And this is not very hard to do. The thing we studied in this particular case was actually motivated by a user survey where designers were saying often they have found a particular font, but it's not quite what they're looking for. They want to take a font and find another font that is a bit happier or a bit more serious. And so since we have a cross-modal vector space, incorporating all this background knowledge of words and how they relate to one another, we can simply do vector arithmetic and arrive at a new target vector and then find the nearest fonts that are closest to that new target vector. And with that, we can answer these sorts of queries. Like in the first example, a font like this, but more elegant. So you see it's a similar font, but somehow has some more curves that make it more elegant. Or in the second example, a font like this, but more fun. You see it's less, it's more irregular, it's more playful. The last one, we look for a font like this, but more professional. And so there you can see it's a bit more serious. It drops some of these unusual icons. All right, so this was just a brief overview of some of the somewhat less conventional work we've been doing here on font recommendation. Now I'll move on to the main part of this talk, which is knowledge graphs for explainable recommendation. So this is especially the recommendation recommender system part is joint work with a bunch of colleagues at Rutgers, where I was working until last year when I moved to Germany. So some of you might know Yongfeng Zhang from the recommender systems community, and also Yikun Qian and Zuahui Fu. So this is an interesting new line of work that we've been exploring in recent years. Let me start just by motivating why knowledge graphs. So some of you might be familiar with decades of work on knowledge representation that didn't really take off that much, but knowledge graphs seem to be quite popular these days. So we believe that one reason is that many modern information systems need to draw on multiple sources of data. These can be different input data sets, different kinds of structured databases. They could be registries. They could be other online reference works. So oftentimes we have different sources, and the information system needs to use all of these sources. In fact, if you go to a website like data.gov, you will see over 200,000 data sets can be found on some of these online registries. So each of these is a separate data set with its own data schema and its own data file format even. So this can be a burden to work with. And so this is one of the reasons why people have been moving towards knowledge graphs, which unify knowledge from different sources. The term knowledge graph, many of you might know, was popularized by Google. The Google Knowledge Graph is basically a successor of Freebase and used also in web search nowadays and for some of the Google Maps services. And but of course, these kinds of graph-based knowledge resources have been existing for much longer. Some well-known ones include DBpedia and Yago, which I also contributed to some extent, and some recently popular ones include Wikidata, which is also used by Siri and many other online services. So there are many public knowledge graphs, but then there are also now, if you attend some of these industry conferences on knowledge graphs, many companies are creating in-house knowledge graphs just to unify all their different data sources and data repositories. All right, so how do we actually go about connecting different data sources in a single knowledge graph? This is a topic I worked on for several years, and it's a quite interesting area that has lots of opportunities and challenges. The basic setting is you have one source of information that might provide certain facts, certain relational facts that you can represent as a graph with labeled edges. So for example, Albert Einstein was born in the city of Ulm. And then you bring in other knowledge sources like a geographical database, further background knowledge sources, maybe also stuff you extract from text. And now the first step in connecting all of these different data sources is figuring out the co-reference. So which items are actually the same across these different databases? What are the entity resolution links? Which items are duplicates across the different databases? So is the Ulm entry in Wikipedia the city of Ulm in Germany, or is it this other Ulm in Montana? These are things you need to figure out, and usually you have some heuristics. You can use the geo-coordinates. You can use all sorts of nowadays neural embeddings you can use to guess which ones are the right matches. And once you have these sorts of heuristics, then you can start comparing entities and choosing the best match. So if I just have two databases and I take entry A1, compare it against all the entries in resource B, then a simple idea would be just to take the one that has the highest probability or the highest confidence score and just take that and discard all the others. And then when I move on to the next entry, A2, and do the same thing, just take the max confidence one. But now I can run into a problem. Both of these are mapped to the same entry, B2. And this would be a problem because this would imply that A1 is the same entity as B2, and A2 is also the same entity as B2. So this would mean that A1 and A2 are actually also the same. They're duplicates, which is usually unlikely, at least less likely than maybe one of these links being wrong. And so the standard way to resolve this is to look at all candidate links, and then you have a bipartite graph and you solve the linear sum assignment problem, finding the max weighted assignment, for example, using the Hungarian algorithm, the Kuhn-Munkers algorithm. But then what we looked at is, what if you have more than just two databases? What if you have 3 databases or hundreds of different databases? And what if some of the mappings are not one-to-one mappings? Then it gets more complicated, more complex. And in fact, you can show that in these more realistic settings where you're bringing together many data sources, the problem becomes NP hard and even hard to approximate, APX hard. And so some of my past work was on solving these sorts of graph problems where you first run machine learning to get confidence scores, and then you find a consistent set. And you can actually, despite the complexity, get certain kinds of approximation guarantees. And so this we then used over the years to create various knowledge graphs, like one is the universal WordNet, where the main focus was taking all these knowledge sources and turning them into one giant coherent taxonomy. And so in this, you can look up, for example, the word Berkeley, and you can see, well, it could refer to the University of California, Berkeley, which is a university, which is an educational institution, or it could refer to Berkeley, California, which is a city, a geopolitical entity, or it could also refer to the namesake of the city. George Berkeley is the philosopher, the British philosopher, and he's of course a person. And so all of this is connected in one big taxonomy for many different languages, and you can basically look up all these different interconnections. This was one major knowledge graph that we created. Others included mining movie scripts, mining novels to extract knowledge about human activities. What does it mean to climb up a mountain or hike up a hill? What are the things involved? And then increasingly we move towards more common sense kinds of knowledge graphs, where we try to characterize what kinds of attributes do objects have. So chili has, in terms of its taste, it has a hot taste in the sense of being spicy, whereas a volcano is hot in terms of the temperature. And this can also already be used for certain kinds of applications, such as set expansion, where you can expand the regular computer style keyboard to find other related products like an optical mouse or a touchscreen. And you can also expand the wall mount type of keyboard, where you find other objects such as a wooden frame or a pouch. And in general, all of these knowledge graphs have many applications. You can come up with search interfaces. You can do question answering, like in IBM's old Watson system. But in recent years, what we've been looking at is how to do recommendation using knowledge graphs. So how do we go about doing recommendation with these knowledge graphs? Well, the way we've been looking at it is you create a knowledge graph with all the product knowledge that you have. This could come from your product database. It could come also from text, so you can extract certain information from online reviews or from other kinds of textual sources, from product descriptions. This is one of the advantages of knowledge graphs, that you can flexibly combine different kinds of information. Even things that were originally in text can often be extracted and then incorporated into the knowledge graph. And so here we actually also incorporate all of our users into the same knowledge graph. It's one big unified knowledge graph that has users, products, and all the relationships. You could also have relationships between users in your knowledge graph. And now to recommend certain items, what we do is we start from the user and then we explore paths in the graph. So you could move from the user to this one product that they already bought and then just move to another related product. So that would be one possible item you can recommend. In reality, of course, there are many possible paths you could choose. And so you need to somehow rank all of these paths and basically also decide which ones to even explore in the first place. And so the way to do that is using reinforcement learning, where basically you have a certain state, mainly the current position in your knowledge graph. And then at each step, you take an action by moving in this knowledge graph. And at the end, in reinforcement learning, or even during your movements, during your actions, you can get rewards. And so in our case, you get the final reward if you end up at a product that was a correctly guessed item based on the training data. And so we investigated reinforcement learning for this knowledge graph setting. More specifically, it's a deep reinforcement learning version where we first learn node embeddings for all the nodes in the knowledge graph. And then we navigate this knowledge graph. We start with the user, and in each step, we have a policy value network that predicts scores for the actions that you can take, the other nodes you could visit based on your current node. And then you do a beam search to find the overall set of paths that you're going to select. And those will end up at certain items. And those items then get recommended. And so this is, of course, a complex recommender system that has a bunch of components. I won't go into all the details. This was published at SIGAR 2019, but it's been used now by many other folks as well, because we made our source code available. So you can also try it out if you want to. The GitHub link is right here. And so this was our main basic approach. And more recently, or first of all, here are some examples of the outputs you can get. So you get certain paths that basically are also explanations. These paths are something you can look at. And although it's using deep learning, you can understand what the network is doing just by tracing these paths and figuring out how we got from the user to a certain product. All right, so more recently, we did some further investigations into some of the challenges with these sorts of systems. One important challenge is that there are differences between the very active users and the more inactive users. It's obviously also related to the classical cold start challenges. The less information you have about users, the worse your recommendations are going to be. But this is also a specific problem in these sorts of knowledge graph driven recommender systems, where we found that not only is there a quality difference, but the model is biased towards certain kinds of paths. And it is not exploring other kinds of paths for these inactive users. So we did some analysis on the Amazon data set, for example, and found that the paths from users to items for the inactive users are a lot less diverse than for the active users. And so this also causes the system then to prefer such kinds of paths when predicting when making new recommendations. It's not exploring all the possible kinds of paths that you might find in a knowledge graph. And so a knowledge graph is an interesting structure because it brings in all this extra knowledge about the products and how they relate to each other. So it is an opportunity to overcome some of the missing information we have about users. We can draw on whatever information we have, but then explore different kinds of paths in the network. And so to ensure that this really happens, we came up with a fair version of our explainable recommendation algorithm. Basically, this is the same kind of algorithm as before, but we add some additional constraints. The constraints are, well, we're still maximizing the recommendation quality, but the additional constraint is we want to have similar recommendation quality for the active and inactive users. And we want to have a similar level of diversity of the path types for the active and inactive users. And so in our evaluation results, we found that these constraints actually also help the overall recommendation performance because there are many inactive users. And so this is not degrading the results much for the active users, but it's helping a lot for the inactive users. And so the overall performance goes up. Some examples of this are seen in this visualization. Here on top, we have our vanilla original path finding algorithm. And for the inactive users, it's often preferring the same kinds of paths. And in our new fairness aware version there, it has more diversity in the kinds of paths that it's using. It's really exploiting more of what the knowledge graph has to offer. And it actually does increase the quality for these inactive users. So it's not getting into just exploiting noisy results. All right, then finally, just one additional slide on a alternative algorithm that we published just this year. So instead of our regular reinforcement learning approach, another alternative algorithm that we've been looking at that is even more faithful in its explanations is to use neural logic reasoning. So some of you might have heard of the traditional Markov logic networks. This is a probabilistic framework for doing reasoning based on input facts, input evidence, and then and you attach probabilities to different facts and then find an overall solution that maximizes the probability. And so there are now modern ways of updating this old framework. And this is something we do in our paper, where we use deep learning as part of Markov logic networks. So essentially, we have traditional logical inference rules, but these are now neural logic models because they are not black or white like traditional logics, but rather they are assumed to hold true. So they all have probabilities. And so we use this framework with the EM algorithm to efficiently find an overall solution. And with this, we again get paths, and the paths have a higher quality, and more importantly, they are also even more explainable because they are actually faithfully explainable. This is a term used in explainable AI, that the explanations you give should really reflect what the algorithm is doing. And so this is the case in this sort of framework. And so for this, we have also made available the source code. I'm not going to go into it much further. All right, then the final part of my talk is about conversational recommendation. And so this is, again, joint work with Zuohui Fu, Yikun Qian, Yongfeng Zhang, and others as well. So this is basically coming back to what I mentioned at the beginning as a desirable property of modern information systems, to not just deliver a solution and then assume you're done, but rather to work with the user in towards solving the problem. And so a typical way of interacting with users nowadays would be to just have a conversational system where the user can provide natural language instructions or questions. And so the first thing we tried in this area was actually a collaboration with a big company that gets a lot of customer service requests. And some of you might be familiar with how these sorts of systems work. You have arbitrary inputs by the users. They can use any sort of natural language. So it's very diverse what you get as input from them. Now, these very diverse inputs need to somehow be mapped to the actual things your system can address. And this could be a frequently asked questions database, or a intent registry where you have, for everything a user might want to do, the possible steps or the possible answers. And so in large companies, these can be quite many possible intents. And the first step is just mapping from the question that the user is asking to these intents. And the user might also proceed in multiple rounds. So what we did was we just reused our same explainable inference, explainable reasoning engine, where we put all the information we have in a big knowledge graph. So this has all the different possible demands that are in the database, all the possible questions that we already have in the database, business units and how they relate to one another. And then we try to go from the input question provided by the user to the actual queries or intents. And so this same approach as before could be used, and the explanations that are available, these paths, can actually be useful, because then you have service staff monitoring what the customers are saying and whether their requests really got answered to their satisfaction. And if not, you need to go back and see where something went wrong. And so you can trace these paths and try to improve your system so that next time similar kinds of requests get a better response. So this was just intent classification. The question is, how do we go then further towards proper recommender systems? And the main difficulty for us was having a good data set. And so what we did was create such a data set for product recommendations, a conversational dialogue data set where simulating the fact that oftentimes users want something similar to a shop assistant. When you enter a store, you might have some vague understanding what you're looking for, but you need assistance from a shop assistant to help you figure out which laptop to buy or which printer to buy. And so we generated such a conversational data set based on the Amazon review data set. Basically, we assume a course to find attribute selection process. So in each step, the system is asking about one attribute, and then the user is just responding with simple answers about that attribute. And for the whole data set, we just used natural language templates. So it's not at all perfect. It's not at all as diverse as real human conversations would be, but it's a first step to make further progress on this product recommendation scenario. And so this data set is available to the community, and we've also investigated deep neural models to solve this sort of challenge. And the models we first created, they were very much based on how the data set was created. So you predict in every step which attribute to ask about and the next question based on this information. And at some point, you can decide to make a recommendation. And all of this is operating over a knowledge graph. So the attributes are items that you can find in the knowledge graph. So this was our first approach. Now our better, more complete approach is this popcorn dialogue engine, also just published very recently at CIKM. Here we have a full dialogue engine. So those of you who know dialogue systems, there you have several different parts. You have a user embedding, you have a dialogue manager, a dialogue state management system. And in our case, we also have a recommendation module that tries to predict at every step which products could get recommended to the user, so it can score user item pairs. And the dialogue state manager needs to make the final decision. At each step, it can decide to ask another question just to narrow down the options a bit more, or it could decide that, well, now it's time to make a recommendation. And so the whole thing is again trained using reinforcement learning. Reinforcement learning is actually often used in these conversational engines. And the rewards for the recommender system are based on the recommendation quality during training and also some of the dialogue aspects. And additionally, we incorporated in this paper also a debiasing reward. So this is to ensure that we look for items beyond just the popular attributes, because when you train these deep neural networks, they basically just go and follow whatever you gave them in the training data. And so with this popularity debiasing, you can encourage them to look beyond the popular attributes to ask about and ask more diverse questions without making too many assumptions, for example, based on the user's history or based on the general distribution in the training set. And so this actually, we show in a lot of details in the paper, increases the quality, the overall quality of the system. Dropping this actually hurts the performance. All right, so this is an overview of a lot of different work we've been doing in this area. The overall vision is that in the future, all kinds of AI devices, Siri and other interactive devices will actually be kind of like recommender systems, because we're always asking them for certain kinds of items, certain kinds of information. And in many cases, we will want to get more detailed advice. And that will take the shape of a conversation where we might ask something like, what's the best insurance for a person at age 60? And then the system needs to figure out what kind of insurance you're actually referring to and clarify the question. And so all of these systems are, in a sense, recommender systems and need to follow these modern paradigms rather than just off the bat recommending certain insurance products. All right, so this brings me to the end of my talk. So in summary, I talked about various different ways of bringing together different sources of information. First, I talked about font recommendation, where we exploit background knowledge from word embeddings and connecting different modalities, fonts, words, and the tag information, which is basically like a little knowledge graph. I then talked about explainable recommendation using knowledge graphs. So first you connect different knowledge sources in a single structured knowledge graph, then you can find explainable paths in this knowledge graph, and you can also ensure fairness while doing that. And finally, I talked a little bit about our ongoing work on conversational systems, our HOOPS data set, which is available for download, and our recent Popcorn dialogue engine. And so if you have further questions, feel free to contact me later on, but now we do also have time for some live questions here at this point.
Thank you, Gerard. Thank you for these very interesting talks. Any question? I remember the remote audience to put some question on the Zoom chat. Okay, we have a question.
Right.
By Giacomo Ballocco. Hi Gerard, thank you for the presentation. I'm a big fan of your works, in particular of PGPR, that I use and explored in depth for my project, and fair, aware, explainable. I have two questions related to these two works. For PGPR, do you think the imbalance of entities can be a problem for the diversity of explanation, and how would we resolve it? And the second question, for fairness aware, do you think that GADU you propose can be expanded to other metrics obtained from the explanation path?
Mm-hmm. So can you repeat the first question? It was about the imbalance of entities.
Yes, the imbalance of entities can be a problem for the diversity of explanation. And how would you resolve it?
Oh, diversity. Okay. Yes. So indeed, we have many different kinds of entities in a knowledge graph, but of course they are imbalanced. So you have certain product categories can be very prominent and others can be a lot less prominent. It depends a little bit on how you implement our PGPR, because we do have certain pruning operations. We don't necessarily need to consider all possible entities that you could visit. We can score, we can trim off some of the entities, some of the possible paths as less interesting. And then you can also, while in your scoring function, you can give them a lower weight. Now, if your training data is, of course, also imbalanced, then they will not necessarily get the lower weight they need to have. And in general, it may be the case that the model learns to certain things from the training data, and then in your real knowledge graph, you have later on even more of such entities. And so it always picks a certain kind of entity. So in some settings, you may need to play around with that and ensure further balancing constraints to downweight the probability that it gives certain kinds of paths. So it's not just an out-of-the-box solution that automatically works no matter how many, how imbalanced your entities are. In certain settings, you do need to play around with it. And that was also what motivated our fairness aware work. And indeed, we believe the fairness aware approach, I mean, this was one study that looked at this popularity or the inactive versus active users. This is one kind of constraint, but the general framework could be easily extended to various other kinds of constraints. So basically, you just need a way to score your possible candidate recommendations, a set of candidate recommendations along these kinds of metrics, and then you could replace RGRU with these other kinds of metrics. It depends a little bit on what kind of constraint you're considering, whether it's easy to do or not. But yeah, I think we would be also happy to provide further details if you email us later on about it.
Thank you, Gerard. Other question? Okay.
Thank you, Gerard, for your very interesting talk. I have a question about, in your opinion, what are the main limitations and opportunities that now we have in exploiting knowledge graph for conversational recommendations?
Oh, for conversational recommendation.
Yeah.
Okay. Well, I mean, a general issue is this connection between the purely neural-based models that can be very strong. Now we have increasingly better large language models, and then the background knowledge. In a knowledge graph, traditionally, it's a very discrete structure. So you have nodes and edges, and so it's a bit harder to represent uncertainty or different kinds of possibilities that may exist. It's very hard to represent a distribution, but it is possible. In our work, we do represent probability distributions over possible paths. And so I think that is the way forward to unify these very different approaches, the purely deep learning based neural language models, even GPT-3 or BART and some of the newer dialogue versions of these models. And on the other hand, the very discrete structures. So your question is challenges and opportunities. Well, it's a very broad question, but in general, I think these knowledge graphs are adding important information, because although GPT-3 is using much of the world's, much of the freely available text that we can find, that we can crawl, there are very large repositories of structured data in every company, all the customer data, all the product databases, all the order databases. So I think we need to somehow keep exploring ways to unify them. And there are also versions of language models that incorporate further entity knowledge to make the connection stronger between the entity IDs and the linguistic utterances. So that is one possible direction. And then if you want something more explainable, where you can trace what is going on, then I would say you should combine that with an explicit knowledge graph behind it. So back it up with this more explicit knowledge. But there are, of course, risks that not everything can be made crisp and discrete.
Okay, thank you, Gerard. Maybe we have time for another question.
Thank you, Gerald, for your very interesting talk. Actually, I have two questions, but I promise that they will be really, really quick. Before you show that you work on neurologic, I would like to ask you if we can expect in the near future some attempts to integrate neurologic with the traditional CRISP logic, and in your opinion, how and when? And the second one is related to the work that was previous to that one. So the one in which you worked on recommendation based on paths in the knowledge graph. So since we work on that, we wanted to ask you if you notice any kind of trends on the path length, or if you have fixed any maximum length of the path for the exploration in the knowledge graph. Thank you, Gerald.
All right. Yeah, very good questions. So maybe the second question first. So we do actually have constraints on the path lengths, because these knowledge graphs are very big, and depending on how you construct them, they can also have a huge fan out. So one node can be connected to hundreds or thousands of other nodes. And so we actually limited the length in all of our studies. In a conversational system, there you have a bit more flexibility, because there you can go step by step and gradually narrow down the set of entities, and also basically make it more dynamic in seeing how willing the user is to continue. Is the user asking more questions or not? So far in our system, we also assume that the conversation will not proceed for indefinitely, but end after a short number of steps, simply because of the combinatorial explosion in the number of paths. The first question is actually also interesting, and in some sense also a bit related, because it's about this whole connection between, your first question was neural logic versus traditional reasoning. And of course, you can already in Markov logic have very simple horn clauses and so on, but you cannot have full logical quantifier reasoning. At least not fully flexible with nested quantifiers. So there is still a gap between these technologies. I wouldn't say that this neural logic version that we have been considering can easily be extended to more complex formalisms, but there is progress in this area. So recently, in recent years, there's been more and more work on taking what used to be just discrete optimization problems and reasoning problems and making them neural. So anything that has a combinatorial explosion can actually be sometimes heuristically optimized by having vector embeddings instead to represent the current search space. So you saw that for AlphaGo, and we are now seeing this for many traditional combinatorial optimization problems that people are exploring deep learning there. And so I think the same thing is gradually also happening for first order logic and other kinds of reasoning, but it's still a very new area, and so lots more needs to happen. But I think progress is being made.
Thank you, Gerard, for your interesting talk and clapping. Thank you.
Thanks.
I think that we can start with the first physical session of this workshop. In this session, we have two contributions, one short paper and one position paper. We start with the work by Alan Stark and Mia Lee, entitled Voicing Concern, User-Specific Pitfall of Favoring Voice over the Text in Conversational Recommender System. We have the speaker, okay. Yes, the slide is. The clicker for you.
Okay. Good morning. I must admit I was preparing this presentation during the conference and I was sort of reusing slides, and then you can see that I forgot to replace the title with the correct title. So everything was okay except that part. Anyway, okay. So we have a position paper. It's called Voicing Concerns. So it's about the pitfalls of always using voice-based technologies over text-based technologies. So that's the actual title. Sorry for the wrong one. My name is Alan Stark. I'm with Wageningen University in the Netherlands and with the University of Bergen in Norway. And this is my colleague, Minna Lee. You might see that the photos are a bit in the same style. We used to be colleagues at Eindhoven University of Technology when we were PhD students. And yeah, why I'm presenting this is basically that Minna and I have been working on chatbots in the past that were, for example, used for social support. So if people are, for example, suffer from depression, that they can find some support with a chatbot. And also that Minna has performed studies where she found out whether people were willing to help a chatbot if it was showing some signals of bad mood, etc. And yeah, since especially Minna knows a lot about chatbots, we were looking at the developments in the commercial domain. See, is it working? Yeah. Yeah. Okay. It wasn't turned on. So what I want today to argue, and it's a position paper, is also a bit of an invitation to have a discussion about this, is that the widespread adoption of voice-based technologies such as Amazon Alexa or Google Home, they might put specific users at a disadvantage, which might be better in using text-based conversational interfaces. Moreover, they also, of course, face some challenges, but we should not abandon them for the sake of inclusiveness. So I didn't want to explain too much about conversational interfaces to, let's say, this audience, because I think you're quite good experts. But it's good to know that there are around 4.2 billion voice-based technologies in use in 2020. And currently are, of course, the voice-based assistants that are very popular. So I'm not sure whether they have been used at the conference, but that might even start happening soon. And I basically want to go through comparing a few of the challenges that both text-based systems and voice-based systems face, and why a few of, let's say, in part the success of voice-based systems might pose some challenges to specific users. So when we look at text-based systems, should I point? Oh, yeah, there we go. So when we think about text-based systems, there are basically two different types. So on the one hand, you can be very query-based. So when you think about Slack, you can send a command and it will respond very specifically. So it's basically sort of let's say, a multiple choice situation in which the user has very specific knowledge about how to use this interface. So if you type unsubscribe in a channel in Slack, it will take you out of the channel. In theory, you could have also have a query like this, get me out of the channel, please, or please let me go. And if Slack would have, let's say, the decent NLP understanding, then it would also might be able to get you out of there. At the same time, the second option, while it is might be more, let's say, intuitive to use or used loosely, it's more prone to errors and misunderstandings. So this might lead that the technologies have to apply conversational repair strategies, so that the let's say the interface on the other hand would need to ask back, well, did you mean X or Y? In essence, this is of course a bit cumbersome, but at the same time, it still leaves, let's say, multiple choice options for the user to choose from. There's not, let's say, there is room for misunderstanding and to resolve it. When we have voice-based systems, they are more open-ended in general. So there may be a confirmatory prompt. So Alexa, for example, might ask for confirmation when you have asked for something. But generally, the queries that you send to, for example, digital assistants are quite open-ended. So if you ask, play me a song for my dinner party, I think this is quite a good example of where a conversational recommender library would be very important, because it's quite exploratory. It wants to fit to the preferences of the person that is using the digital assistant. There is, of course, a lot of environmental noise when you have such open-ended questions. So when you're thinking of a digital assistant in a car, there's a lot of noise of the car itself. There might be multiple persons in the car. You as a user are multitasking. So when you're sending queries, you might not be focused in articulating. So there are a few issues that speech can suffer from these things due to the environment. Well, furthermore, these are more like contextually related, and you could argue you can solve that technically. But there are also persons for whom it is just quite difficult to actually express themselves clearly. So if you suffer from stammering, if you have a very, if you speak, for example, English with a bit of an accent, and you want to use a digital assistant, it might not comply, because these digital assistants are, let's say, designed for the mainstream user. So the data sets that are typically developed, they are validated with, let's say, American users that provide American input, and it is then cross-validated. So perhaps I'm not a native English speaker. I guess there are other people who are also not native speakers in the room. Sometimes we might be misunderstood by such voice-based technologies, and that can be frustrating. And sometimes you can do a simple fix. So there's like a paper in tourism for people who have accessibility issues that you constrain some input, but this is more difficult in conversational technologies, because it sort of hits the essence of the interaction. So what we basically suggest is that the technologies that are to be developed, that they are more like voice enabled rather than voice based, so that there is always an option to use text, because text, as I've shown earlier, as more this, let's call it a multiple choice option that is very closed-ended, that the misunderstandings can be resolved if there are any. And I think it's also important to validate with data sets with imperfect data. So I wanted to highlight here an example that's called Project Euphonia. It's now actually by Google being implemented. So I think here there's a video on the website. There's also a link to this website in the paper. And the man, I think, suffers from multiple of MS. I'm not gonna try to pronounce it. And therefore his speech is being impaired quite severely. So the more severe MS is for that man, the harder it is for use to any voice-based systems or technologies. So what this project, for example, does is that it collects data or asks people who have, let's say, identifies having any speech impairments to submit sentences to the system. So that they, for example, record phrases that are commonly used for commands, so that it will be easier for such technologies to retrieve and match, let's say, such imperfect sentences for other users that also have disabilities. So this, let's say, is one example of how it could be mitigated. And I think we need more work along those lines, and also keep on working on text-based systems. So that's basically what I wanted to, let's say, share to think about this, that this is still a thing and that we should not, let's say, myopically only focus on the voice-based technologies. And I think that I know a lot of persons who stammer, and yeah, it's sometimes the first time and it's funny to see them use Alexa or something, but yeah, no, in the long run, it can be very frustrating for them. So I would also like to help my friends who suffer from that. So thank you for listening, and love to take some questions if that slide will show up.
Question from the audience?
Any question from the audience? From remote audience? Nothing?
Thanks. Tom Vollebrecht. I guess you could extend the voice and textual to visual as well, because I've noticed that there seems to be a strong drive towards replacing visual with text or voice, whereas in fact that reduces the capability to communicate quite significantly.
Yeah, no, that's I think it's a very good point. I think also like in scenarios where we are multitasking, that yeah, while I'm talking, I'm doing a lot with my hands, of course, and I guess that's also a very intuitive way of communication, and yeah, also important for people who are deaf to it will be, they need like more visual and textual ways. I think for them it's also intuitive, so I think it's a good suggestion. That I don't know if there are many, let's say, visually based interfaces like in digital assistants yet. I don't think so, but I think it would be good to work on those as well.
Okay, thank you. Other question? Nothing? Okay, thank you.
Thank you.
Now we have the second work of this session. Work by Gianmaria Biancofiore, Tommaso Di Noia, Eugenio Di Sciascio, Federuccio Narducci, and Paolo Pastore, entitled GUAP, a knowledge-aware conversational agent for job recommendation. And we have Federuccio Narducci as presenter.
Thank you, Claudio. Good morning. Today I'm in the twofold role of co-organizer of KaRS and presenter of this work that is GUAP, that is about a job recommender system. My co-authors are Giovanni Maria Biancofiore, Tommaso Di Noia, Eugenio Di Sciascio, and Paolo Pastore. So in this, for this specific task of job recommendation, generally we have two main approaches that we can exploit. One is based on an information retrieval paradigm, another on a recommender system. In the first case, generally we have a user query and the system is able to retrieve the most relevant documents for that query. In the second case, we have a recommender system, a well-known recommender system that is able to filter out items that are not interesting for the user. In this specific work, we adopted a conversational recommender system that has the main characteristic of interacting with the user through natural language sentences. So another advantage of this kind of recommender system is that the user preference elicitation is incremental. This is GUAP, our system. We have 5 main components. So is a job recommender system that is able to model the user preferences in order to recommend to the user the most interesting job calls. And in particular, in cold start situations, WAP is able to exploit the data coming from the LinkedIn profile of the user. The first core component is the orchestrator, that is a sort of hub of our architecture. For example, it manages the interaction between the different components. In the case, for example, the user asks for a recommendation, the orchestrator will invoke the recommender system in order to generate the recommendation for a given user by exploiting the information stored in the user profile. The second component is the chatbot, that is the interface between the user and the system. So we have implemented the chatbot is based on Dialogflow that is powered by Google. And in particular, there are two main components in the chatbot: an intent recognizer that is able to identify the goal of the user given a sentence, a natural language sentence, and the entity recognizer that is able to extract the real world entities in the sentence, in the user sentence, for example, the name of a place or a university and so on. We have naturally the recommender system component. In this case, the approach is really simple. It is based on the vector space model. So we have an Elasticsearch index that stores all the job calls. So when we have to generate a recommendation, the system computes a similarity between the user profile in terms of scales, preferences, and so on, and the representation of the job calls in the Elasticsearch index. Doesn't work. Okay. Sorry. Okay, we are at user profile. The user profile is the component that extract and models the user, the information about the user. As I told before, it is able also to extract information from the LinkedIn user profile. Then we have the crawler. The crawler daily update the database of the job calls extracted from the Gazzetta Ufficiale, that is the official journal of the Italian government. Next, we have the knowledge graph. This is a very important component of our application because it models and represents the information coming from DBpedia, for example, the locations, the places, and so on, and other information coming from the ISTAT website, that is the official Italian website about statistics and so on. And the knowledge graph allows us to have a finer grained conversation with the user, because we can have some negotiations in the case the user is not satisfied by some particular recommendation. This is just an example of how WAP works. In this case, we have a recommendation that is a job as a full professor in the computer engineering field at the University of Rome Tor Vergata. But in this case, the user is not particularly satisfied by this recommendation, So the system asks the user what is flexibility in terms of topic of interest for that specific job. The answer of the user is not so much. So in this case, the system understands that we can move up to one level in the knowledge graph, in the job categories hierarchy. And in this case, so the new recommendation is about a position as electrical engineering that is just one step close to the previous recommendation. So, in conclusion, WAP is a platform for recommending jobs in the Italian public administration. We exploit explicit knowledge coming from knowledge graphs, in particular DBpedia, and a knowledge graph that we built by using the Instat website. One of the main characteristics is that we have an incremental preference elicitation, and there is the possibility of negotiate a recommendation that doesn't satisfy the user needs. As future work, we want to introduce a more effective ranking function instead of the vector space model adopted now. And we are designing an in vivo experiment for evaluating how the system works. Thank you.
Thank you, Lucio. Any question from the audience or from a remote audience? Okay, I have a question about the in vivo experiment.
Yeah.
How did you have in mind to conduct this kind of experiment? Some guidelines or some direction that you would like to?
Yeah. For this kind of systems, the only possibility is to carry out a user study, because there aren't data set that we can exploit. So we are designing a user study, and we want to compare at least 3 configurations. One with a simple model based on an information retrieval system, so without personalization. Another one with WAP without the information, the knowledge coming from the knowledge graph. And the third one, the complete configuration that is with WAP, with the conversational interface, and the information of the knowledge from the knowledge graph.
Okay, thank you. Other question? Yes.
Thank you. Are you also planning to examine like longer term effects? So perhaps whether, people actually, the things that they choose, maybe for jobs that they actually take them, or whether they, whether they do actually something with these recommendations.
Yeah, actually, we can evaluate these aspects only when the system will be used by real users, because now I think that the only opportunity that we have for job recommendation is provided by LinkedIn, that according to our skills and profile generally suggests job opportunities. So this is the novelty of our approach, is the interaction that we guess is more user-friendly by a conversational interaction. So we have to evaluate it in future, I hope. Thank you very much.
Okay, thank you. A question from the remote audience? No? Okay, I think that we close this first session. Thank you. And we have a break until the 11:30, and then we start with the last session. Thank you again, and see you later.
Okay, we can now start with the last session of the KaRS workshop, and I can welcome our next session chair, Antonio Ferrara. Please take the stage. Have a good session.
Good morning, everybody. So welcome to this fifth session. And let's start with the first talk, Adherence and Constancy in RecSys Explanations for Recommendation. This work is by Vito Walter Anelli, Alejandro Begiochin, Tommaso Di Noia, Francesco Maria Donini, Vincenzo Paparella, and Claudio Pomo. So please, Claudio.
Hi, I'm Claudio Pomo, PhD student from Politecnico di Bari, and this is our work in collaboration with the Universidad Autónoma de Madrid e Università degli Studi della Tuscia, entitled Adherence and Constancy in RecSys Explanation for Recommendation. Recently, the theme of explanation artificial intelligence has come to foreground and capturing a lot of attention in the community of the machine learning and related communities, and also fields closer to the social science. This trend has also touched the research of recommender system. And the explanation for recommendation play an increasingly important role in the interaction between user and recommender system. The explainable recommendation is a task that aims to provide a suggestion to the user and the reason why the recommender suggests a specific item to a generic user. A classical example could be the Amazon interface, in which you can see something related to your last basket activity or your activity on some items, review and rating, and Amazon try to figure out the reason why you receive this kind of suggestion. And this is a common example. In this kind of modeling, we can divide two main approaches. The first is the model intrinsic approach for the explanation, for the explainable recommendation. And in this case, we have directly the explainable model inject into the recommender system, let's say. So the pipeline provide in the output a recommendation with explanation. So the role of the recommender is twice. You feed the recommender system with the user profile and the item catalog. The magic, let's say, in the recommender system provide in the output the recommendation for the user alongside with the explanation. But this could lead some problem in the performance of a recommendation, because maybe the task is not fitting better only the elaboration of the score and the list of the recommended items, but also involve the task of explanation. So maybe this is a trade-off and could be affect the performance of accuracy. On the other hand, we have the model agnostic approach, and in this case, the pipeline of the recommendation is untouched. So the first part in this slide, as you can see here, is the classical recommendation pipeline, user profile, item catalog, recommendation engine, and the output is the classical recommendation list for each user. After this stage, you can introduce these explanation methods or explainable module that provide you explanation separately from the task of recommendation. And in this case, the user could ask to the system, why you suggest me this specific item, and you, via these explanation methods, provide the reason why the recommendation is provided to the user. Or maybe, if you intend to a global explanation with respect to the system or the list for each user, you can provide the reason why some items are suggested to the user. So we have a local explanation and a global explanation in front of different point of view that the user interact with the system, let's say. One of the most interesting and promising approach for the post-hoc explanation and the model intrinsic approach is LIME. And LIME is a local interpretable model agnostic explanation. And the idea behind these methods is very, very simple. We want to provide, from an instance that we want to explain, a model, an explainable model, in a lot of cases, some linear model, that reconstruct the original performance of the black box model, let's say. And this kind of operation is provided by sampling around the object that we want to explain a sort of neighbor of instance that provide to the explainable model the performance that are matched as close as possible to the black box model. With this, in this aspect, an important role is played by these terms, that is measured the distance between the original instance that we want to explain with respect to the neighbor that we have sampled in the training set. But these kind of methods suffering from some of locality perturbation, because some studies in explainable artificial intelligence fields demonstrate that is not stable when we time to time change the neighbor or change the function that collects the neighbor. So this is one of the first interesting findings that move our search. Following, we saw that there are an implementation of LIME in the recommended system fields, named LIME RS. In this case, the author provide a lot of and very interesting suggestion about the sampling of the item that are useful to provide and to feed the explainable model. Because if you have in mind a classical scenario with the domain movie, a user could receive a recommendation. Maybe the first item in the list is Titanic, and the user can ask, why you recommend me Titanic? The idea behind LIME RS and the sampling is similar to the LIME approach, but in this case, the sampling could be retrieved a real point of the dataset. With respect to the original approach in LIME, when you can provide a sample also with the synthetic data, in this case, is not possible. Is not useful to provide some inconsistencies a point of the catalog to train this simple model to generate the explanation. So the author provide a very clear example about that in that work, and also we can understand that in recommended system domain, this kind of approach is very important and is the more challenging for this kind of explanation methods. And another important findings is related to the implementation of this kind of methods, because when we go deeper in the analysis of the code of this approach, we saw that the sample strategy is driven by the popularity of the item. But, as you can imagine, this kind raises a big problem, because if you sample alongside the popularity, this could be introduce or amplify some biases also in the explanation part. And we have posed ourselves these two questions. One is about the constancy of the LIME RS, and another question about the adherence with respect to the reconstruction of the original feature of the items that we want to explain to a specific user. and we provide two different metrics to approach this research question. The experimental setup is quite simple. We use three well-known datasets, Movie Lens 1M, Movie Lens Small, Yahoo Movies, with the respective categories for the items in the catalog. We use two simple models, attribute item KNN and vector space model, and we use Elliott as evaluation framework. We optimize this model with respect to NDCG. And we try to understand how Lime provide the explanation. In particular, we generate top 10 for each user, and we consider only the first item in the top 10 for each user. And we generate for this pair, user and item, the explanation with LimeRS. The output of the LimeRS is a weighted vector, where G is the category of the film and W is the weight that Lime consider for a specific category. And we sort this vector in a descending manner, in order to have on top the feature, the category that most affect the recommendation, the explanation for the user. And we repeat this kind of operation, the generation of the explanation, 10 times in order to explore if time to time the behavior of Lime remain the same or changing over the time. This is the big idea behind our work. So for answer to the first question about the constancy, we explore this 10 generation of explanation for each user in order to understand if for each user the performance of Lime remains constant over the time. So for a specific user, we consider the 10 generation of the explanation for the specific item, the first item, sorry, in the top list, and we investigate how many times the first item, or the second item, or the third item until the fifth item remain in the same position across the 10 runs experiments, because we want to provide some findings about the stability, let's say, of the LimeRS across the time. And we introduce this kind of measure that average the possibility to the system to provide in some specific position of the final weighted vector the category that most affects the recommendation. This is the results, and we saw in this table that the value equal to 0 means that the category provided by LimeRS in the first key position is always different, so is the worst case, while when this measure is near to 1 means that the category provided by LimeRS in the first key position are always the same. And we have two different behavior with respect to these two different methods. Firstly, for the attribute item KNN, we saw that there are some interesting consideration until the third feature in the final explanation vector. After the third position, we have a sort of a toss a coin, because the probability decreasing a lot and reach quite 15% for the for the Yahoo movies. But for the vector space model, the behavior is completely different. And in this case, the generation of Lime in combination with this kind of model seems to be more stable. Indeed, we don't reach until the fifth position of the category for the explanation worst results. After we discuss about this kind of finding. For the second research question, we provide this measure that try to estimate how many times Lime is able to reconstruct the original feature belonging to the item. In this case, we want to investigate how many times Lime is able to put in the top 3 of the final weighted vector for explanation one or more feature that belonging to the item, one or more category, movie category that that Lime is able to reconstruct based on the sampling. Also, in this case, we divide the results between the two models, and we can see that for the attribute item KNN, we reach the best performance for the movie lens 1M, and in this case, the value of 1 is the worst case, and the value of 0 is the best case. We saw that in the 75% of the cases, Lime is able, for the first feature in the weighted vector, to reconstruct the category of the just one category of the items that we want to explain. This behavior is different for the vector space model. In this case, and in particular for Yahoo movies, vector space model could be a very, very interesting and reliability performance. And the reason why of this behavior and this difference is the main findings that we reach in the end of this work. Because as you can see in this table, the results of attribute item KNN and vector space model alongside these metrics for the 3 dataset are not very exciting. The reason why behind these results is the dataset and the side information quality that we added to this dataset. And this kind of problem, let's say, this kind of drawback affect also the recommendation. So from one hand, we have the Lime characteristics to is not very, very stable, let's say, along the sampling, because time to time Lime could choose a different neighbor, and these neighbors are chosen alongside a popularity-based distribution. And also the model and the quality of the data affect a lot the performance of the explanation, let's say, from this kind of point of view. Constancy alongside the 10 rounds and adherence of obviously the property of the Lime's RS to reconstruct at least one feature of the original item category. Okay, so we conclude to some interesting further investigation point. We want to understand if with some different model, some different more prominent, let's say, model for recommendation, this kind of findings are confirmed or not. And we want to investigate also what impact the structured knowledge could have on this kind of performance in terms of constancy and adherence. So thank you for your attention.
Thank you, Claudio, for your interesting presentation. Is there any question from the audience? Some question online? Okay, I have a question. Which could be, in your opinion, the impact of the structured knowledge on the recommendation explanation?
Obviously, as you can see also this morning during the keynote by Gerard de Mello, I think that the impact of the knowledge on this kind of approach could be very variable, because if the findings are confirmed, we try to provide this same experiment with other different models that take into account structural knowledge, and maybe the results of recommendation are very, very different from these poor results. And I think that this these new results could be affect a lot the final explanation part, also in terms of adherence and constancy, because I think that if we model the system in a good way, in a way that the feeling between user and items are very, very appealing, also the explanation could be have a different performance, let's say, from this kind of point of view.
Okay. Okay, so
Thank you,
Claudio. Okay, so let's continue with the second presentation. It's a short paper by Giandomenico Cornacchia, Federuccio Narducci, and Azzurra Ragone, entitled A General Model for Fair and Explainable Recommendation in the Loan Domain. Lucio will present the work. Thank you, Lucio.
Okay, I'm here again. So I'm presenting this work that is a joint work with EY Business and Technology Solution, and is about a loan recommender system. So what is the problem? The problem is that nowadays AI systems, algorithms, make decisions really important for our life. For example, a mortgage grant or a job call and so on. But the problem is that these algorithms can discriminate according to some characteristics. For example, the gender or the race. And so they can also amplify these social or ethical issues. The other problem is that generally these systems are not able to provide an explanation of their decisions. Furthermore, in this financial domain, recommender systems are really common, and in particular, they are exploited for recommending the right financial product among different services of different financial providers. But in this specific domain, recommender systems have some requirements. In particular, they have to adhere to some regulations. They have to follow, they have to implement fairness criteria, and they have to explain their decisions. For the specific task of loan recommendation, this task consists of finding the right product for a given borrower that first is able to satisfy the user financial needs. And second, this loan will be paid back by the borrower in the future. So in this work, our proposal is to define a model for a personal loan recommender system that is compliant with the European regulations, that implements fairness criteria, and that is able to provide explanations about its decisions. In particular, as yesterday Nathalie in a very interesting talk shown, there are different classes in which the AI systems are classified. And in particular, AI systems that compute credit score or evaluate the creditworthiness of a given user are classified in the high risk category. Furthermore, there is the GDPR that define this right to ask for an explanation. So in this specific case, the user has the right to give an explanation about an algorithmic decision. Then, about the fairness criterion, we need that our algorithm doesn't show any prejudice or favoritism towards a group of people or specific person, in particular related to some characteristics such as the gender or the race and so on. So, but the question is, how can we sure that the decision of a loan recommender system is fair? The solution that we propose is a simple solution in terms of idea. It is not simple in terms of implementation, and is to provide an explanation of the loan recommender system decision. But what is the problem of providing an explanation for this specific task? Is that generally we have black box models. So it is not possible to analyze the flow that conducted to the decision of that specific algorithm. So we have to adopt some model agnostic methods for generating the explanation. So a model that is not dependent on the specific machine learning algorithm that has been adopted. How these tools work? They define a surrogate model that simulates the original one. In particular, we adopted this third-party tool that is SHAP. SHAP is inspired to the concept of shapely values. So each feature in the decision-making process is a sort of player that contributes in different way to the final outcome, to the final result. In order to define what are the features that give the different contribution to the outcome, SHAP performs a random set of combinations of these features. This is the output, an example of output of SHAP. So we have a list of features, and for each feature we have a score that represents its contribution in the specific outcome. The problem is that this kind of explanation, in our opinion, is not so easy to understand for a common general user. So we define this model. This model can be applied in a conversational scenario. So we have the user with that applies for a loan. This loan has some characteristics. The amount is 16,000 euros. The duration is 24 months. So there is the machine learning algorithm that is making the decision about the application characteristics and the user profile characteristic, for example, the income and other characteristics. There is the decision accepted or rejected. At this point, we can use the output as input of SHAP that will generate a ranked list of features with associated a score. Now we can use this output obtained from SHAP for generating a natural language explanation. In this case, the explanation is the credit amount is too high based on your salary, that is a characteristic of the user profile, and the duration is too long, that is a characteristic of the loan application. There is another step that is useful for suggesting to the user some corrective actions for modifying the application in order to get the loan. In this case, there is this perturbation that try to modify the application, the loan characteristics, in order to find the closest example that is able to get the loan. In this case, after this perturbation step, we are able to generate this counterfactual explanation that consists of a set of corrective action. In this case, is to reduce the amount to 10,000 euros and to shorten the duration to 18 months. The model for generating this natural language explanation is, is really simple. We defined a set of rewriting rules. So we defined a sort of context-free grammar. And so in conclusion, in the financial domain, there is still a lot of work to do for having algorithms fair, transparent, and explainable. There are some third parties tool, but in our opinion, the explanation that they provide is not user-friendly. So we propose this solution for generating natural language explanations, and furthermore, we propose this model for generating counterfactual explanations that can help the user in reaching her goal, that in this case is the loan. Thank you for your attention.
Thank you, Lucio. Is there any question? No, no question. Some questions from the audience? Yeah, of course.
Thank you for a very interesting talk. I think this topic is interesting and also really important. I may have a question regarding those explanations in natural language. Yeah. I understand that you will, there is those SHAP scores translated into the natural language. Then there was some module, some perturbation. Yeah. And can you provide us a little bit more of a detail of this model, whereas this converts the natural language into counterfactual explanations? Because as far as I understand that the counterfactual explanations is what to do to break the results, to reverse the results of the model. Exactly. So which score of the SHAP needs to be lowered. So could you provide us a little more detail about that? Thank you.
If you can share again the slides, please, because I have an example of generation of natural language explanation. Okay. So as I told before, there are, we defined this set of rewriting rules. So for example, in this case, we start from this term that is the explanation, and we can replace the explanation or with a sentence or with a sequence explanation, conjunction, and sentence for a more complex explanation. So this is an example. We have this natural language explanation, that is the credit amount is too high based on the salary and the duration is too long. In that case, what is the template that we can implement for generating this explanation? This explanation is composed of these terms. A feature, that is the credit amount, a verb is, an adverb to, an adjective I, and a motivation. That is one of the rules that we defined, is that one. Okay, so what is the problem? That we have to choose the adverb to, the adjective I. For deciding what is the adverb that we have to adopt, we define some mapping rules between the score of the set value. For example, in this case, we have that the amount has a very high score, 0.8. So in this case, we define that if the score is in a range, for example, 0.7, 1, the adverb is high. So there are, it is difficult, this task, because you have to define a lot of rules by hand. And so this is the result. For the counterfactual explanation, the model is the same. The only step that we need to do before is to perform this perturbation of the parameters of the loan application. So in this case, the system tries to apply different application with different parameters. And when it finds the closest example to the user application, it suggests to modify the application with these new values. This is the main idea behind our model.
Okay, another question, Nara?
Thank you for the talk. Just a simple question. So for the perturbation and the counterfactual explanation, is it done on the original model or the surrogate model that is explainable?
On the original model, or?
Or the surrogate model that you can explain with the...
On the original model,
okay.
Yeah.
Yes.
It's the same algorithm that is exploited for the counterfactual explanation.
Okay. Okay, we have no more questions, I guess. Okay, thank you, Lucio, for your talk. Okay, let's continue with another long paper entitled Case Study on the Development of a Recommender for Apple Disease Diagnosis with a Knowledge-Based Bayesian Network by Gabriele Sottocornola, Sanja Barik, Fabio Stella, and Marcus Zanker. So please come here. Thank you, Gabriele.
Thank you, Antonio. So, welcome everyone. I'm Gabriele Sottocornola, PhD student at the University of Bolzano. And today I'm going to present this knowledge-based recommender system for the diagnosis of Apple disease. So, as you might know, Bolzano province is a quite large production region for apples, and also at worldwide scale, apple is the third most produced fruit. So one of the main causes of economical losses in such a production system is the one of post-harvest disease. So that disease which occur during storage of the fruit. Thus, our goal is to develop a decision support system to recommend the diagnosis of such a post-harvest disease and possibly suggest countermeasures. In this slide, I'm going to present the big picture of such an expert system. So imagine that a user with an infected apples comes to the system, which is interfaced with the web app, and the system proposes a set of questions related to the macroscopic symptoms of appearing on the apples. So the user might or might not answer to this question, and given the answer, the system adapts a new set of questions. After a certain number of loops, the system stops the feedback collection and output a list of recommended disease together with the natural language explanation, which is our diagnosis. In order to build such a model, we need to construct the knowledge base for such a diagnostic process. And so given that no data were available, we rely on interviewing an expert in the domain. Specifically, we started from this small owl ontology in which simply it is described that the apple has a specific disease, as an apple part which is affected by some specific symptoms. So we enhance this description of the phenomenon by adding 30 random variables in a Bayesian network format to represent the diagnostic process. Furthermore, we need to specify the quantitative parameters of our model that in the case of a Bayesian network are the so-called conditional probability tables, which represent the relationship of the symptoms with the disease and the stage of the infection. In order to elicit these probabilities, we rely on frequentistic questions to be asked to the expert. So in the end of this process, we produce such a Bayesian network in which, very briefly, the two parent nodes are the disease and the stage of the infection, and which are never observed by the user. And in particular, the disease is our target variable that we want to predict. All the other nodes represent symptoms variable, which are instead directly observed by the user. Given the knowledge base, and so the Bayesian network model, we produce such a recommendation mechanism. So imagine that a user comes with the target apple, which is infected by an unknown disease, and so the system incrementally elicits the evidence set to be fed into the Bayesian network by asking questions to the user. When the evidence set is constructed, the Bayesian network easily computes a posterior probability distribution over the disease hidden variable, and thus each disease in our set has assigned a diagnosis score, which is again the posterior probability of this disease di with respect to the evidence extracted. And thus a ranked list is completely defined for recommending a disease for the apple A. Nevertheless, in such an expert-based or knowledge-based model, the problem of transferability might arise. In this context, it might exist a mismatch between the expert-defined probability to build the Bayesian network and instead the probability which are derived by the user interaction with the system. In order to cope with such a problem, we introduce a virtual node OI for each symptom variable SI, which has the same set of value of SI. And thus we define the likelihood evidence as the probability of the variable OI conditioned on the SI. in order to estimate such a probability, we apply a very simple method which allows to directly estimate those probabilities through the so-called consensus, or the probability of observing a specific value for OI, given that the expert-defined value for that set of apple was Sij. So to validate such a system, we had to rely on user studies, so in vivo analysis, and in particular, we exploit a set of users that were challenged to use our system in order to identify the correct disease on a bucket of simulated target apples. So the apples were simulated via a set of photographs, and ground truth disease were determined in a laboratory. The evaluation of the system was based on the recall of the top K recommended diagnosis by our system. And specifically, we perform 3 different user studies that differ one to the other based on the level of expertise of the involved user and the number of apples involved in the analysis, and of course, the number of users involved in the study. So in the first one, a very expert user in the domain of apple disease was challenged to diagnose 21 apples using our system. In the second study, again, a single expert, in particular a student involved in an internship lasting 3 months, was challenged to diagnose 131 apples. Finally, in the last study, 11 bachelor students in biology used our system to identify the same set of apple of the first expert of the first user study. In this table, I summarized the result for the vanilla expert-defined Bayesian network, so without any fine-tuning or likelihood evidence technique. And in this case, you might notice how for the single expert study, the system performed incredibly well, so close to perfection already from the recall at 1 measure, while the performance decreased for the single user study and get really worse for the multiple user study. So we understood that such a decreasing in the performance might be due to this transferability problem. So at first, we wanted to analyze the contribution of different attributes with respect to the diagnostic performance. And in these 2 graphs, we reported on the x-axis the set of attributes of our system ranked based on the agreement of the user in MUS with respect to the ground truth symptom value defined by the expert. So the curves represent the performance of the system by incrementally including the attributes, so from the easiest one to the hardest. And interesting to notice, for example, in the recall at 1 and recall at 2 curves, that the model, including all the attributes, is definitely outperformed by more simpler models, including just 7 or 8 attributes. Vice versa, in the single expert evaluation, we notice how the performance are linearly increasing, and this means that the very high performance of the model that I showed can be obtained just by including all the attributes that we defined in the first version of the system. And in this last table, I'm going to compare with respect to the MUS evaluation, the performance of the vanilla model with respect to the performance of the model fine-tuned on the same set of data with respect to a maximum likelihood algorithm, and then the performance that I show in the graph to the a posteriori selection of the best attributes and the likelihood evidence technique. The interesting insights in this table are that the improvement from the simple Bayesian network to the trained one are quite limited, whereas in the likelihood evidence technique, we see a significant improvement of the performance. And in some cases, like RecCollet 2 and RecCollet 3, the performance are similar to the a posteriori selection of the best attribute. So to wrap up my talk, I just presented this knowledge-based recommender system for diagnosing post-harvest disease of apple, and the system was built by based on a Bayesian network model with the parameters and the structure of the network being elicited by qualitative assessment on expert interviews. This model, despite showing a very high theoretical diagnostic accuracy, might be affected by transferability problem, which severely affect the system performances. And likelihood evidence seems to be a valid technique to address such a problem, and so bridge the gap between a different environment and so cohorts of users with different expertise. Finally, I want to mention that an ongoing work that I'm currently working on is to hybridize such an expert system with a picture-based interaction with it. So thanks for your attention.
Thank you, Gabriele. Thank you so much. Is there any question from the audience? Online audience? Okay. Okay, I have just one curiosity. Mm-hmm. Are you, like, given the good results that you had with the single expert user, mm-hmm. are you planning to study other ways to transfer that knowledge?
Yes, so we try to apply some causality computation in order to bridge such a gap. Mm-hmm. And okay, more or less the likelihood evidence was the technique which performed better in our experiments. So the one that we keep showing and improving.
Okay, thank you.
Thank you.
Thank you again. Okay, so let's continue with a short paper now called Ligan Recommending Artificial Fillers for Police Photo Lineups. It is by Patrick Dokupil and Ladislav Peshka, maybe. Okay, Patrick, thank you.
Thank you. Okay, so does it work? Yeah. Okay. Hello, everyone. My name is Patrick Dokupil, and today I will be presenting our paper about generating and recommending fillers for construction of police photo lineups. This is a joint work of me and Ladislav Peshka, and we are both from Charles University in Prague. The main motivation of this work is to simplify the process of constructing police photo lineups. And police photo lineup is basically a grid of images that is used for eyewitness identification of a suspect, where the witness is given a sequence of images. One of them is being suspect, and the rest of them are so-called fillers. You can see example of police photo lineup here. And the crucial part of these lineups is the similarity between the fillers and the suspect. because if the similarity is, let's say, too low, so that the suspect stands out, we basically end up with something that is called bias lineup, which is here. And in that case, it is a problem because even like highly uncertain witness can easily identify the suspect based on just some really general appearance characteristic, like for example, age. And on the other hand, if the similarity is too high, we end up with a lineup of near clones, which is also a problem because in that case, it is very difficult to reliably indicate the suspect. And our goal was to basically simplify the whole process, because as it is now, there's problem with searching for fillers, because in RecSys, it is typically done manually. And so it is very time consuming. And second, the image databases that are used for searching the fillers are typically small, and there is a lack of like suitable fillers. So we would like to solve these two issues by using a generative model that would be able to generate like artificial images of the fillers and recommend them to the user. The proposed LIGAM framework consists basically of three components. One of them is fill generation, which is responsible for generating images of the fillers. Another one is a recommender system that is basically responsible for generating or recommending latent vectors for the fillers. It takes suspect on the input and returns a set of latent vectors for the fillers. And last part is web application, which should simplify the process of the construction. Okay, so I will start with fill generation. I should mention that this part is rather complex, so I will describe it just very briefly, and you can find all the details in the paper. So we started by training StyleGAN2 on our custom dataset. That custom dataset was based on images of missing persons from databases of Slovak and Polish police. And once we have trained the model, we just took its generator component and used it as our generative model, basically. And then the, let's say, key property that we are exploiting is that, or maybe I should mention that for those who don't know GANs, in GANs it typically works in a way that the generator takes latent vector on an input and generates an image from it. And we exploit a property that close latent vectors in the latent space correspond roughly to similar images. And thanks to that property, we basically, to exploit that property, we need to be able to obtain latent vector for the suspect image. And in order to do so, we have decided to train identity preserving encoder, which for a given image returns it latent vector representation. And this basically allows us to perform, let's say, reconstructions of the input images, which you can see here. Also here you can see the results of our trained generator. Okay, and yeah, okay, so once we are able to generate the filler, the question was how to get the latent vectors for the filler images. And basically, we decided that this should be the responsibility of the recommender. And sorry. Yeah. Yes, okay, so, okay, and basically we started with, let's say, approximation or naive idea, which was to take the d-dimensional ball in the latent space around the suspect and sample the latent vectors on random from it. But this was quite problematic because even though it worked in some way, we didn't know how to properly set the radius of such d-dimensional ball so that the generated images are like in the have a meaningful similarity, because the radius of the d-dimensional ball basically acts as a parameter controlling the similarity between the images, the fillers, and the suspect. So if the radius was too high or too large, we would end up with images that were too dissimilar from each other or even degenerate. And on the other hand, if the radius was too small, we would end up with just clones. Okay, so I hope it is better now. And yeah, so because we weren't able to decide which value to use for the radius, we basically decided to do, let's say, a small trick of splitting the d-dimensional ball into several, let's say, distance ranges, and then learn the distances online. And to better illustrate this, consider this example where we split into the circle and into bands. And basically each band can be then represented by a single recommender, which samples latent vectors from its corresponding band. And the bands form like increasing sequence of distances. So which means that, let's say, recommender number 2 generates images that are strictly less similar to the suspect than those recommended by recommender number 1. Okay, so yeah, and because we need to recommend several images, so for each recommended item or position, we select the recommender based on Thompson sampling procedure, and this set of the recommenders is actually dynamic, and the user is able to ask dynamically for more or less similar fillers using feedback buttons that are available in like user interface. Using these buttons corresponds to shifting the recommenders in one way or the other. Okay, and I should also mention that by default we use the suspect as a center around which we sample, but as the user continues selecting the filler, we sometimes use one of the already selected fillers as the center on random with some small probability. Okay, so another component is the web application. It is just simple web application which allows the user to upload suspect and generate and recommend fillers for it. And the user is then able to select appropriate fillers for the lineup. And once the user is satisfied with the lineup, we can download the lineup. We also constructed simple user study where the respondents were given a sequence of images, and their goal was, or task was to distinguish between generated and real images. And the results were that the accuracy was around 60%, meaning that the users or respondents were just slightly better than guessing on random, so it was quite good. We also saw some patterns in which images were least frequently and most frequently identified. What is quite interesting is that the most frequently identified were those with uniform look and, let's say, uniform background, while those least frequently identified had some kind of bluish background looking like old passports. And the conclusion is that we explored, let's say, a new domain of recommending artificial items in criminology domain, and we built a reasonable proof of concept application which allows to simplify the process of lineup generation, although it is still not perfect. There's like a long way to go to make it production ready. And yeah, that's basically all from me. Yeah.
Thank you, Patrick. Thank you. Please. Okay. Do we have some question from the audience or remote audience? No? Okay. Just a curiosity, do you think that a similar approach could be applied also to other domains, for example?
Yes, I think that we can probably use similar approach. I know that recommendation of artificial items is probably used in fashion domain. Yeah, where they recommend, let's say, new clothing styles and so on. So I can think maybe we can do some adaptation to other domains also.
Okay. Thank you again, Patrick.
Thank you.
Thank you. So before going on, I remind to the remote audience that they can submit their question via the Zoom chat, and then we will read them for them. So let's continue with another long paper that is called A General Aspect Term Extraction Model for Multi-Criteria Recommendations. This work is by Paolo Pastore, Andrea Iovine, Fede Lucio Narducci, and Giovanni Semeraro. And Andrea will present it for us. Thank you.
Thank you. So, good morning. I'm Andrea Iovine. I'm a PhD student from the University of Bari in Italy, and today we'll present our work titled A General Aspect Term Extraction Model for Multi-Criteria Recommendations. So thanks to the diffusion of platforms such as Amazon and TripAdvisor, we have access to a large quantity of text reviews about products and services, which describe the strengths and weaknesses of these items. This information can be integrated into our recommender systems in order to improve the performance. Specifically, aspect-based sentiment analysis is the technique that is used to extract the opinion of the user to contain in a text review. In particular, the opinion usually is referred to several characteristics of an item, which are also called aspect. So, in particular, aspect term extraction is the subtask of aspect-based sentiment analysis, which is concerned with extracting the linguistic expression of an aspect inside a text review. Training an aspect term extraction model is challenging for several reasons. First of all, supervised models require large quantities of annotated data in order to work. Moreover, this annotated data must be domain-specific, and that's because aspect terms vary significantly from one domain to the other. Moreover, we have the problem that currently only very few resources are available for this task. For this reason, the objective of this work is to investigate domain adaptation strategies that can enable recent deep learning-based models to extract aspect terms from reviews without the need for domain-specific annotated data. Moreover, we want to assess the impact that this domain adaptation strategy has on the quality of the generated recommendations. For this purpose, we have developed an aspect-based recommendation framework that is able to extract aspect terms from reviews without the need for domain-specific annotated data, then group aspect terms into categories, and then exploit the information, exploit the aspect-based ratings set by the system in order to improve the recommendations of a recommender system. The architecture is made up of several modules, the first of which is the aspect term extraction module. The ATE module is tasked with extracting aspect terms from text. In particular, this is treated as a sequence labeling task in which each word in the sentence is classified as either being part of an aspect term or not. Specifically, we have implemented several deep learning-based models in order to perform aspect term extraction. So we have combined the bidirectional LSTM model with Word2Vec, Grove, and Elmo embeddings, as well as we use BERT for this task. For the domain adaptation strategy, we first train each model on data coming from multiple different domains and then test them on a dataset of reviews coming from a previously unseen domain. So our hypothesis is that these models will be able to learn the domain-independent characteristics of aspect terms which can be used to classify aspects in an unseen domain. Then the aspect clustering module is in charge of grouping together aspect terms that refer to the same concept. And that's because aspect terms, the same aspect, the same category of an item can be expressed using different linguistic expressions. In this case, we first find a representation for each aspect term using their Word2Vec embeddings, and then group aspect terms together into categories by using a clustering algorithm such as k-means. The sentiments analysis module is in charge of assigning a sentiment score to each of the aspect categories that were discovered in the text review. And specifically, we have used the Vader model for this. So the final output of this part of the framework is a set of user item, aspect, sentiment, tuples. For generated recommendations, we have employed several multi-criteria recommender system algorithms. So we implemented two distance space algorithms, which are the multi-criteria user-to-user and multi-criteria item-to-item collaborative filtering algorithms. And we also included the multi-criteria SVD, which is an aggregation function-based model. Basically, we train an SVD model for each aspect category in the domain, and then we predict a score individually for each aspect, and finally we use an aggregation function in order to aggregate the aspect-based scores into the final scores, for example, by computing the average of the aspect level scores. So we performed an experiment in order to evaluate the domain adaptation strategy proposed in this work. So we have divided this experiment into two parts. First, we evaluate the aspect term extraction models themselves, and then we evaluate the impact on the quality of the recommendations. So the objective of this experiment is, first of all, to assess the impact that this domain adaptation strategy has on the quality of the recommendations. And second, we want to compare our framework against a set of baselines which are based on single criteria recommendation. For the aspect term extraction model dataset, we have used the ATE models that were described earlier and tested them on 6 different datasets, which come from the domains of restaurants, laptops, hotels, computers, speakers, and routers. The test is also divided in 2 parts. We first did a single domain test in which each model is trained and tested on the same domain, and then a domain adaptation test in which we first train each model on 5 different datasets and then use the remaining datasets as a test set in order to simulate a situation in which we have no access to domain-specific training data. For the ATE model test results, we can see that the model based on the bidirectional STM with Elmo embeddings actually outperforms the others in 5 out of 6 datasets. We can also see that the BERT-based model is particularly sensitive to training data size. As we can see, the model performs worse on the smaller datasets. Finally, we can see that the Word2Vec and Grove embeddings instead are performing poorly in domain adaptation tests, which means that they are less suitable for transferring knowledge about aspect terms across domains. So, in order to perform the recommendation test, we have added another dataset, which is the Yelp recruiting computation dataset, which is a dataset of restaurant reviews containing around 230,000 reviews. So we first extract aspect level ratings from this dataset by using 2 variants of the BiLSTM plus Elmo model, one that was trained using all 6 ATE datasets, and the other which was trained without restaurant datasets, so in order still to simulate the lack of domain-specific data. So we grouped then the aspect terms into 10, 20, and 50 aspect categories, and finally, we have generated recommendations. And the objective of this test is to evaluate the accuracy of these models in terms of rating prediction accuracy. So we have, again, we have employed the multi-criteria recommendation algorithms that we have described earlier, and also compared them against a set of single criteria baselines. So recommender systems algorithms that are based on single criteria ratings. From the recommendation test results, we can see that if we train the aspect term extraction model without domain-specific training data, we often incur a small decrease in the performance of rating prediction accuracy, which can be explained by the fact that the model, in this case, usually extracts a more sparse set of aspect level ratings. However, this is not always the case. For example, for the multi-criteria SVD model, we have observed that the model trained without restaurant reviews actually performs slightly better, which also is true for the fact that the multi-criteria SVD outperformed the distance-based algorithms by a fair margin. When comparing against the single criteria baselines, we can see that the multi-criteria algorithms that we included outperform their single criteria equivalent. And this is true even when we don't have access to domain-specific training data. We can also see that all the differences that are recorded here are statistically significant. So, in conclusion, we can say that the domain adaptation strategy that we have employed in this test, in this work, is definitely effective in extracting aspect terms and also in improving the quality of the alpha recommender system, even if we don't have access to reviews that come from that domain. We can see that the domain adaptation strategy itself does cause a decrease in performance overall, but the decrease is fairly small. As future work, we propose to continue this investigation by adding more datasets and more domains, and by adding more aspect term models, architectures, and other multi-criteria recommendation algorithms. So thank you for your attention, and I'm ready to take your questions.
Thank you so much. Thank you, Andrea. Thank you. Is there any question from the audience? Okay, okay, Andrea. Just a question. As for the domain adaptation task, how did you manage the choice of the dataset in that case?
Okay, the choice of the datasets. So the choice was mainly made by selecting the dataset that we had access to. So we're talking about those 6 datasets. So one thing that I should add that in this test, we have performed actually 6 different domain adaptation tests, because we had to basically use each dataset as a test set individually. So for example, we tested the model on the restaurant domain. Then we tested the model on the hotel domain and so on. So we had basically 6 tests. And at the end of this test, we just averaged the accuracy metrics for each of the 6 tests. I don't know if this is the answer that you were looking for.
Yeah.
Okay, thank you.
Thank you. So thank you again, Andrea. Thank you. Okay, now we have again a long paper named Improving Media Content Recommendation with Automatic Annotations. It is by Ismail Arrando and Rafael Tronci. Okay, we have Ismail here.
Hello, everyone. My name is Ismail Arrando. I'm a PhD student from Eurocom. I'm presenting a work that I did supervised by Rafael Tronci, and it's titled Improving Media Content Recommendation with Automatic Annotation. So media recommendation, as you know, probably multimedia content is probably the fastest growing content on the web as the number of video on demand services grow, as every platform or social media has video sharing features. And so it makes sense to focus on recommendation in this domain. And we also see that usually multimedia content, such as YouTube videos or documentaries or podcasts, tend to be thematic or topical in nature. So people who are interested in watching a certain sort of kind of content would like to see similar content, which is not necessarily applicable in all sorts of recommender systems. For example, if a user would like to buy paper towel, it doesn't necessarily make sense to recommend other paper towel products. So it makes sense to consider this recommender problem in the context of content-based recommendations. So content-based recommendation is when we try to recommend items based solely on the similarity of their content and not necessarily leverage any information we have about the user statistics of viewership, which is more the collaborative filtering approach to it. So this is very useful for the cold start problem. So when you have new content and you don't have any users feedback yet, so it makes sense to just find items that are similar to what the user would have viewed and recommend them. And yeah, so and it also makes sense for the kind of applications there's privacy issues or anonymity. So you can only base the recommendation on the content itself. But the challenge in this case is to find a representation of the content that would make this recommendation easier or would give us a similarity measure that we can use for recommendation. So there are multiple approaches, usually text-based or graph-based. And for this application, we'll focus on the graph-based recommendation. So the main approach, at least the most straightforward one, is to construct a knowledge graph based on the available content. So we represent every recommendable item as a node in a graph. Then we connect or link these nodes using some sort of metadata. For example, the genre, the keywords, topic, etc. And then we use some kind of graph embedding to represent each of these items in an embedding space. And we use this semantic similarity in this embedding space to approximate a similarity or the recommendation for the user. And so the challenge in this case would be to annotate these this data. So how can we take this content and build this knowledge graph out of the data that we have? So our proposal is to use automatic annotation. So basically we have a lot of tools in the NLP and the information extraction literature so that we can use off the shelf. So it doesn't necessarily require any training or extra annotation or human effort. And this can be used for free. So you can just use available tools and at scale. So because it's automated and you don't need to have human annotators or archivists. And so for example, we have name entity recognition, topic modeling, and keyword extraction, which are the ones that we focus on in this paper, but also you can use all sorts of tools that you can find in literature, such as facial recognition or similar models. And for our evaluation, we use the TED dataset. So the TED is this event where people are invited to give speeches or talks about different topics. And usually it's between 12 and 20 minutes for each talk. And the data set has over 1,100 around 1,150 videos that are tagged with metadata. So we have things such as the title, description, the speaker name, and some tags such as theme and topic or keyword, I think. And then we have also the user interactions. So we have two kinds of interactions, the favorites. So people can interact with the video by adding it to their favorite list. So it's like liking on other social platforms, or we have comments. But for our application, we'll focus on I'm going to go to that in the next slide. And so, yeah, basically the particularity of this data set is that we have two kind of ground truth for evaluation for recommender system. On one hand, we have the user preference. So we call this task 1, or the viewing history. So basically we have users who already liked multiple videos, and we can use this to see whether the video that we recommend kind of corresponds to what the user watched in previous viewing sessions. And then we have the content relatedness ground truth, which is basically we have human editors who would watch the video and then would recommend or like would list several videos from the TED catalog that are similar to what the user has just viewed. And so this would give us a more kind of content related evaluation rather than just user based one. For the experimental setup, which we use for all the experiments, the basic idea is to start by creating a knowledge graph connecting the talks using the existing metadata. So we have some metadata available in the data set. And then we concatenate all the textual metadata that we have to then use all NLP tools to extract these other descriptors. So this is the kind of automatic annotation part of the approach. And then we add this extracted descriptor to the knowledge graph that we already had. And then we compute knowledge embeddings, knowledge graph embeddings, and measure the similarity between the knowledge graph embeddings to generate the recommendations. And again, we have two evaluation setups for the two tasks. The first task is the history-based one. So we take the history of the user, we remove one item, and then we recommend up to 10 items. And we try to find whether the item that we removed falls within this list of recommendation. But the second one is the kind of more interesting in our case, which is the content-based one, is that for each talk, we take the embedding corresponding to this talk, and we try to find the closest items. And if the ones that were recommended by the editors, so the human annotated ones, fall within this list of recommendation, we consider this a hit. So these are the kind of the formula for the two things. And for the task 2, because the relatedness or the editor's suggestions are not always, so we have between 1 to 3 recommendations. So to accommodate for this variety in the number of related videos, we just divided by the number of ground truth hits that we have. So just we have a score that adds up to 1 in the end. Yes, so for our experiments, we did not focus that much on the embeddings used, because this is not necessarily the thing we're optimizing for, but we just tried multiple available embeddings or like graph embedding algorithms, and we found that the best performance were given by TransD, and so we used it for the rest of the experiment, although this could be just probably due to the kind of hyperparameter fine tuning. So this is another kind of focus. So the first kind of automatic annotation that we use is topic modeling. So again, we use just a simple model, LDA, and we try to play a little bit with the hyperparameters. So for topic modeling, we don't necessarily know how many topics we have in data set. So this is a hyperparameter. We divide it between 140 and 100. And then we have also a kind of a confidence score that is given by the topic model to each of the assignments. So a talk has a specific topic by a certain confidence or percentage. And by varying these two hyperparameters, we get different results. But as I kind of forgot to highlight it, but the best results were given by keeping the number of topics as 40 and the threshold at 0.3. And surprisingly, we see that more or less the results on both tasks are kind of similar. So whatever works on the kind of content-based recommendation also kind of seems to work on the user-based recommendation. And also another note is that the number 40, the number of topics, is kind of similar to the number of tags that we have in the original data set. So the closest we are to the actual number of topics in the data set, the better the results will be. You can also see if we are very much off the results, the performance could actually be lower than the original graph without any added topic annotation. The second one is keywords. So this is also used an off-the-shelf keyword extractor. And we see that, again, if we add all the keywords that we have a lower drop of performance because we have a lot of noisy keywords. But if we filter out the ones that are not too, that the model is not too confident about, we get increase in performance on both hit rate and MRR and on both tasks. And finally, I did main entity recognition, and it seems to perform, like at least increase the best in terms of hit rate between the original and the added knowledge graph. And again, here, if we filter out the named entities that are not too frequent or rare, which is probably noise in the data set, then we increase the results even further. So finally, if you add everything together into the graph, we see this improvement in the overall task, about 12% in the hit rate between the baseline and the added annotations, and then 8% increase in the task 2 under the content-based recommendation. So in conclusion, we see that automatic annotations can help us improve the results of the recommender system without any extra cost, basically because we're using off-the-shelf NLP models. And the approach seems to improve not only the content recommendation, but also for even the general user-based recommendation. And finally, there's an emphasis to be made on the hyperparameters of each of these tools, because if it's not tuned correctly, it could actually hurt the overall performance because of the noise coming from the automatic tools. And for the future work, basically there's the complementarity. So there are many representations that we can use for this content-based recommendation, and we've already have some promising early results. And basically, if we combine the textual representation with this graph representation, we actually can push the performance even further. Multimodality, because we're talking about multimedia content. If we can use the other modalities, it can give us even further performance. In the case of TED Talks, it's usually one person speaking, so it's not necessarily very interesting in terms of visuals, but in other tasks, it could be very interesting. And finally, the explainability, because this is all is built on top of a knowledge graph. We can use the approaches that we've already presented in this workshop or others to kind of give a layer of explainability to the user. So that's all, and thank you for your attention.
Thank you, Ismail, for your very interesting presentation. We have a question from the remote audience, from Mirza. Could you please elaborate on how you form connections between graph nodes? Basically, given the nodes, how do you decide if a link exists between them?
Okay, so as I said before, so I'm going to just go back to the slide about the experimental setup. So we're starting from the list of all the talks that we have in the data set, and we connect them by the shared metadata. So in the beginning, we have something like genre and speaker, etc. But like once, for example, 2 talks mention the same entity, so we have an entity recognizer, and it says like, for example, I don't know, US of A or United States or something, then this is a common node we add to the knowledge graph, and both talks link to it. And we do we do the same thing for keywords or topics, etc. So we just find this common metadata and we create links by connecting each entity, or like each talk that mentions or like has similar metadata by this straightforward link, basically. Okay, this answers the question.
I think so. Okay. Okay, another question.
Hey, thanks for a real great talk. I'm wondering, it's a question/comment. Okay. Did you consider, or could you comment on whether your approach might be useful also for trying to recommend like sub-item, not the whole video, but perhaps just a scene from the video or something like that, and whether your approach is possible for it, or whether you perhaps look for it in the future?
Thank you for the question. Yes, this is a very actually, this is a very concrete use case. So, for example, for news broadcasts, usually we have a lot of segments in the news, and only one of them that would kind of cover a specific topic. And in this case, yes, the main approach was actually we had kind of started working on kind of like segmenting the contents before and then like doing the linking the sub parts instead of the big part. But in the case of the TED Talks particularly, it's usually one common theme. So it didn't make a lot of sense to do this. But yeah, this is definitely it makes a lot of sense for many applications to segment first, do like automatic content segmentation, and then do the information extraction on the segments instead of the whole part. Yes. Thank you.
Other questions? Okay. Thank you again, Ismail. Okay. So let's go now with the last presentation, a long paper named Conversational Recommendations for Job Recruiters. It's by François Mente, Zoltan Miklos, Sébastien Hervieux, and Thierry Roger. We have François here. This one. Moment.
Do we have to do
could you put in full screen? Okay.
Okay. Hello, everyone. So I'm François. I'm a PhD student at the University of Rennes, France. And I'm doing my thesis in a company named Alten. So I'm going to present a conversational recommender system for recruiters. So basically, our system will take a job offer, it will take a resume, and it will extract skills from those, map them into an ontology, so which can be seen as a knowledge graph. And it will produce a score which will represent how a resume can match a job offer, and an explanation which is dependent of the model. It's not a model agnostic explanation. So the recruiters, which is a user, can make educated feedback, so the system can fine-tune the recommendation and hopefully find someone to fill the job. So Alten is a consulting company, so it has to find consultant for its clients. It has a lot of recruiting to do, so it's a key task for them. There's a few specific to doing recommendation for recruitments. We can't really learn over time. We're not making a recommendation for a user like we usually do. We're not recommending items like movies to someone who probably watched dozens of movies previously. We are making the recommendation for a job offer, and once we found someone for the job offer, it's most likely over. We want to put someone else on the same job offer. So by doing conversational recommendation, we hope that the system can quickly learn what is needed for the offer, and we can quickly find someone who fills the offer. So we have at Alten we have a lot of data. We have a resume in the form of structured resume. So it's easy to extract information from those resumes. Those resumes contain a list of previous professional experiences, and those experiences also contain a list of skills which we'll use to make the match. So it's a content-based recommendation. We don't have those resumes aren't matched with a job offer already. So to build a matching data set, what we did is that we took the last experiences from those resumes, and we said it was our job offer. So we now have matching set between a resume and the offer. So we can evaluate easily our model. We also want to build a negative appearance between a resume and job offers. So what we did is that we took a resume, and we took
an offer, an experience from another resume, and we said it was an offer, but it was a wrong appellant. So the system has to discriminate between which are positive appellant and which are negative one, so we can evaluate our model. So regarding the ontology or knowledge graph we used ESCO, which is a multilingual classification of skills, competencies, and occupation. It's made by the European Union. It's composed of over 13,000 skills and almost 3,000 occupation. In orange, we have a part of the skill ontology, and on the side in the green, we have a part of the occupation ontology. So it's directed acyclic graph, as we can see. Each of those nodes possess labels, a preferred label and a few alternative labels. And we use those labels to learn how to map skills into the ontology using a BERT model. So regarding the way to make the match with the ontology, so once we mapped the skills from job offer and from the resume into the ontology, we can compute a similarity between two skills. So we just look at the depth of the deepest common ancestor. So, and we look at the total depth of the ontology, and this is how we computed the similarity between two skills. And once we have similarity, we can compute the similarity between two skills. We can associate skills from the offer with most similar skill from the resume, and produce a score. This is easily explainable. This is entirely engineered, and it's based on the ontology which is understandable by a human, so it can so the user can fine-tune the query to have to have better recommendation if the first batch of recommendation doesn't fit his need. So to include user feedback, we added a weight to the skills of the offer, which represent how important the skill is for the offer. So, for example, if the recruiter has a first set of recommendation and he has a recommendation, someone is recommended, but it doesn't exactly find its need, and it looks at the explanation, it's because of the skill, certain skill is present, and it finds the skill not this important, it can lower the score and have lower the weight of the skill and have a new batch of recommendation which doesn't consider the skill as important as previously. So since we have a matching dataset, we compared our system based on ontology to a deep learning system, and as we can see here, the deep learning which we use BERT, so it vastly outperforms the ontology-based one, but those results doesn't take into account the conversational aspect. So it's for every skill with a weight of 1, and we don't have a user interaction yet to see how the conversational aspect would impact the result, but we tried to make a few random weighting for the offers and see how much it could impact recommendation. And the best case scenario, it could go up to 87%, which is similar to the deep learning system, but we have we don't know if the recruiters could actually find weighting who would match would be that good, and we would have to do some in vivo experiment to validate this hypothesis. So here is what the explanation could look like. So this is a graphical explanation. It's not necessarily the best form. Sometimes textual explanation may be more efficient. It has also to be experimented. So we can find the skills from the job offer, skills from the resume, how they were matched between each other, and we can also look at how two skills are related in the ontology, so the user can clearly understand how the match was made. And for now, it can just change weight of the skills in the offer, but we would like to add more action in the future. Like it could say those skills aren't well related this way. If there is a mistake, they can have a mistake in the ontology, or maybe they are related like this, but they could they're not as close as it may seem. So it could either weight to the edge, etc. So for future work, so as I said, we would like to complete potentially the ontology. It's not necessarily as specialized as it should be for the fields of at Alten. We would like also to improve the mapping between skills to the ontology by adding labels to the ontology. And most importantly, we would like to run an in vivo test campaign to see how the recruiters would actually interact with the system. And we would like to evaluate the difference between the deep learning and the ontology system with the user, not necessarily just objective measure like efficiency and or accuracy, but also subjective one like the trustworthiness of the system and the engagement the user could have with the system. Is the explanation this important for this kind of job, or is the accuracy the only thing that matter? Thanks for your attention, and I'm ready to take your question.
Is there any question from the audience? Okay.
Hello, thank you for an interesting talk. I wonder, I'm not familiar with this knowledge graph you're using, but are there also some kind of, let's say, soft information, for instance, size of the company, or whether things around the culture that is imposed by the company, which might be relevant for the one who's seeking for the job, and it, in the end, may let you match better?
So no, I don't have any information about. I can have the name of the company for which the job is, but I don't have information regarding the company, like the size or the field. But yeah, it could be integrated in the future, and we could also imagine a company ontology, which should add even more knowledge to the system.
Thank you. Thank you. Other questions? Okay, so thank you again, Francois. Okay, this was the last presentation. So thank you for attending this session. And now I give the stage to Walter for the closing of KaRS.
Okay, thank you all. It was really a really interesting session with knowledge graphs, conversational agents, and everything. But this is also the end of KaRS for this year, ComplexRec and KaRS workshop. And this is the reason why that was a really successful workshop with a lot of contributions, and we are receiving emails asking for your papers. And I read that also in the chat, there is a question on this side. So I want to say that in this moment, Casper is working for the proceedings, and he has already prepared the proceedings to be sent to Sarah. And in the meanwhile, during the next week, we will put all your papers and the slides, obviously, on our website. And we will talk with the RecSys organizer to have the recordings of the different talks, and we can split them and put them on YouTube or whatever, so that all the different attendees can follow your presentation. And also we received requests in this sense from the American North and Southern American guys before this session, because this kind of time zone is not so comfortable for them. So they asked us for the recordings of your presentations. And in the end, what I want is to thank all the other organizers, the ComplexRec organizers and the other KaRS organizers, because without their effort, we would not have this kind of a successful workshop this year. But the most important thing for me is to thank all the authors, because the core of the ComplexRec and KaRS workshop are your work. So a clap for all the authors. And I would like also to thank the attendees for the question and all the emails that we are receiving about the papers. And please, this is a message for the authors and the attendees. Please continue to send us and to send to the authors your question, because the real goal of this workshop is create connections. So thank attendees for all your work and all your questions. Thank you. And see you the next year.